All right. Hey guys. So you, at this point, like you should have got the warm up, and you should have like spent about 10 minutes working on this. If you haven't done that, pause the video now and do that. Once you're done or you're kind of stuck, now press play. Okay. We are starting with kind of a review from last class. We're finding all the roots of a polynomial. So our first step is to list all the potential rational roots. That would be the factors of the constant term, -1, over factors of the leading coefficient, 4. So that would be plus minus 1 over plus minus 4, plus minus 2, and plus minus 1. So we have, that would be like plus minus 1, plus minus 1/2, and plus minus 1/4. Those would be your 6 potential rational roots. To find the actual rational roots, we're going to plug them in here. So we'll find f of 1. So we'll plug in 1. We'll get 4 times 1 to the 4th plus 3 times 1 to the 3rd minus 3, 1 squared minus 3 times 1 minus 1. And this all comes out nicely to 0. So that means that 1 is a root, right? X equals 1. That's a root. And same thing for f of -1. So f of -1 goes in 4 -1 to the 4th plus 3 -1 cubed minus 3 -1 squared minus 3 times -1 and then minus 1. And this also comes out to 0, which means that x equals -1 is a root. So once we have 2 rational roots and we have like a quartic function here to the power of 4, if we synthetically divide it, we'll get down to a quadratic, and then we can use quadratic formula. So we're actually done at this point. Like I don't need to try the remaining factors. Sorry, the remaining potential roots. Okay, so we're gonna do we're gonna do synthetic division here. So I'm gonna put 1 here, 4, 3, -3, -3, -1, and then synthetically divide. So 4, 4, 7, 7, 4, 4, 1, 1, 0. And then I'm going to do it again, but with -1. 4, 7, 4, 1. So 4 down, -4, 3, -3, 1, -1, 0. So what I'm left with is 4x squared plus 3x plus 1. And now I'm going to use quadratic formula to find my last roots, right? I mean, this doesn't look factorable to me, so I'm going to use quadratic formula. So we're going to do -3 plus or minus the square root of 9 minus 4ac, so that's 16, over 8. That is -3 plus or minus root -7 over 8. And I can take out the root -1, so to get -3 plus or minus root 7i over 8. So now I have my 4 roots. So these are imaginary roots here, so they're not going to be visible on the x-axis down below. But let me just write everything out. Here we have x equals 1, -1, -3 plus root 7i over 8, and -3 minus root 7i over 8. And then my y-intercept is 0, 1, right? 0, -1 from above, right? We plug in a 0, we get -1. So when I'm graphing, I'm gonna plot the x-intercepts that are real. So I'm gonna have 0, -1 down here, like 1, 0 here, -1, 0 here, and because of the way the graph, like because we have a positive leading coefficient and an even degree, like it's gonna end like this. So we can guess that the polynomial is going to look something roughly like this. Okay, and like it doesn't have to be exactly right, but this is like a general idea of what it could look like. The other thing that you'll see in your homework are these number lines. The number lines, we did this when we were doing like quadratic inequalities, and this is where we test points in between these values to see if it's positive or negative. So if you test them like a 0, like a number between -1 and 1, you'll get a negative value, right? When I plug in a 0 in here, I get -1, right? F of 0 is -1. That means that the function is going to be negative between those values. If I plugged in like a 3, f of 3, up here, you would get a positive value, right? which means that it's going to be above the x-axis at that region. And same thing over here, if you plugged in f of -3, you'd get a positive value, meaning that it's above the x-axis in this region. So this is like a verification. Sometimes you're not given like enough information to fully graph the polynomial, so that's why we do the number line. Okay, let me pause that. Okay. So we are now on 3.6. I'm going to start with like a little definition, and then you're going to have just a 10-minute activity. So we're doing rational functions. This is our last new content of the unit. What are rational functions? So rational functions are fractions. They're functions that are fractions where the numerator is a polynomial and the denominator is also polynomial. This is a rational function. Okay, so in this like exploration work you're gonna do, you're given a rational function here, x squared plus 2x minus 8. That's shown to the right. You're gonna complete a table, talk about the domain, talk about the x-intercept, and so on, and to sort of figure out, well, how does this rational function kind of tell me that information? Just to kind of get you started, like for x, for -4, my g of x would be 0. That would be your first table. So take 10 minutes, work on this, and then play the video again when you're done. All right, so you've taken 10 minutes to work through this. Let's fill it in. So for -1 here, we are undefined at -1, right? There is no function output. We call this a vertical asymptote right here. 0, we've got like roughly 4 at 2. Notice how we have this open hole here at 2. I know it's kind of hard to see, but there is a little hole there. That is also undefined. That is not defined. That openness, this, I know I'll expand that. That is not defined at that point. And then 5, roughly 1.5. Okay. The domain of g of x. So we can say it's all numbers from -infinity to -1, then from -1 to 2, and then from 2 to infinity. That's my domain. So I'm taking breaks at -1, where I had the vertical asymptote, and at 2, where I have the hole. Okay? We have one x-intercept. What is it? Well, I can see here it's at x equals -4. X equals -4, that would be -4, 0. What is happening to the graph at x equals -1? So I mentioned earlier that this is called a vertical asymptote. And why is that happening? So this this happens when, well, if we were to plug in a -1 into here, if you were to find g of -1, you would get 1 minus 2, you get -9 over 0. So it happens when we divide by 0, we get this characteristic. Okay? So we want to explore these features further. We're going to factor the numerator and denominator. So the factored form would be x plus 4, x minus 2 over x minus 2, x plus 1. Okay, Carlos argues that g of 2 is 0, but Lau says g of 2 is undefined. It is undefined because it is an open circle, open hole at that value. So it is undefined, and like you could verify that if you found g of 2, you would actually get 0 over 0. This is an undefined outcome. Even though we have 0 in the numerator, this is an undefined outcome. Okay, but it's a different outcome, like in terms of a characteristic, right? 0 over 0 looks a lot different on the graph than a number over 0. A number over 0, like a non-zero number, creates that vertical asymptote, whereas 0 over 0 creates that open hole. Okay, so 6 is kind of asking us to put it all together. What is the relationship between the factors and these features? So if we think about it, like, let's start with the x-intercept. My x-intercept is at -4. Where do I see like a -4 in this factored form? It's in the numerator, right? It's a solution. So the x-intercept is a solution of the numerator. Okay? What about the vertical asymptote? So I have a vertical asymptote at -1. Where is -1 in this function? Where's the -1? That's in the denominator. So the vertical asymptote is a solution of just the denominator. And then this is called a whole. The whole is at x equals 2. How does my x equals 2 represent? How is that reflected in the fraction? It's in both the numerator and the denominator. So the whole is a solution of both. Okay? So here are three characteristics. X-intercept is a solution of the numerator, vertical asymptote, solution of the denominator, and whole is a solution of both. Okay, I'm going to pause it for any questions. Okay. All right, page over. We're on the formal notes. Okay, so we have these three. These are kind of all like x features. Okay, so we have the x-intercept. That's gonna that's when the graph, or so the function touches the x-axis, right? So this is our x-intercept. The x-intercept happens when only numerator equals 0. So what's the only value that would set the numerator equal to 0? So I have x minus 3, x plus 1, and then x plus 1, x minus 2 on bottom. Okay, so if I set the numerator equal to 0, x minus 3, x plus 1 equals 0, I'm going to get two solutions, x equals 3 and x equals -1. Okay, one of these is an x-intercept, one of them is not. Which one is the x-intercept? It's only 3 because -1 appears in both the numerator and denominator. This is not a solution. So again, it's only numerator. Okay? That is the x-intercept. So when only the numerator equals 0, you're going to have an x-intercept there. Vertical asymptote. Vertical asymptote happens when we are dividing by 0. So, for example, it can look like this. It can also look like this, with both going the same direction up or same direction down. And this happens when only denominator is 0. Okay, so we're going to set the denominator equals 0, x plus 1, x minus 2 equals 0. I would get two solutions, x equals -1, x equals 2. Again, only one of these is a vertical asymptote. Which one is it?
2.
It's only 2 because -1 appears in both. This is not a vertical asymptote. This is only denominator. Okay? Then we have wholes. So wholes on that last activity, they're sometimes hard to see, but the function doesn't change its pattern. It just keeps doing what it's doing, but there's just a single point, like a single undefined point. Undefined point. Okay? But it looks like it didn't change the function, right? So how do I identify this? We set both equal to 0. So if we set both equal to 0, like you would see, well, x minus 3, x plus 1 equals 0, and x plus 1, x minus 2 equals 0, which is the shared solution to both the numerator and denominator? Which one happens to both? That's x equals -1. So the whole will happen at the x value -1 because that is in both the numerator and denominator, right? This is the key. It's at x plus 1, x plus 1. So that's the solution. Right? We don't care about the -3 and the -2. It's in both the numerator and denominator. But then the question is, well, how do we find the y value? You got to pay close attention because this is very important. To find the y value, we go back to that rational function and we cancel out the common factor in the numerator and denominator, and we rewrite the expression with the simplified numerator and denominator. we then take that x value that we found and plug it into this. Okay, so we're going to plug in the negative 1 into this expression. So we're going to get negative 1 minus 3 over negative 1 minus 2. That's going to be negative 4 over negative 3, which is the same as 4/3. That means my y value is 4/3. So whole would be negative 1 comma 4/3. Okay. All right. Just as like a little example, here we have x minus 2 over x squared minus 2x minus 3. We want to make sure we factor the bottom. So we'd have x minus 2 over x minus 3, x plus 1. Here, I would have an x-intercept where? My x-intercept would be what? X equals 2. My vertical asymptotes, plural, would be x equals 3 and negative 1. Would I have any holes? No, because nothing appears in both the numerator and denominator. Okay, that's it for the x features. Okay? All right, I'm going to turn the page. We're going to do the horizontal asymptotes. Good? Okay, all right. So, what are horizontal asymptotes and slant asymptotes? So these are, we talked about the horizontal. The horizontal and slant asymptotes determine the end behavior. Okay, so like a function, a rational function can do like all these different things, but at the end of the day, it needs to approach that horizontal value when it goes to infinity. So like this is my horizontal asymptote, this like horizontal line here. And you can see like in the middle, I'm crossing it. I'm allowed to cross it many times, however many times I want to. But what matters is as we go towards the edges, as we go to infinity and negative infinity, I have to get closer and closer to that value. Okay, that is a horizontal asymptote. Make sense? Slant or oblique asymptotes are really similar. They're equations that the function approaches in the long run. So it could look something like this. But like, unlike a horizontal asymptote where it's where the horizontal line, it's like a linear. This is a y equals mx plus b. Whereas a horizontal asymptote will just be a y equals b. Right? It's just a horizontal line, whereas the horizontal asymptote is a linear equation, like it has a slope. So how do we find these? This is like the end behavior. How do you find the end behavior? We look at the degree of the numerator and denominator to find the end behavior, because that will tell us kind of what's going on. There's three situations. We have bottom heavy, even, and top heavy. In bottom heavy, we're going to look at the degree of the numerator and denominator here. The degree of the numerator here is 1. The degree of the denominator is 2. When the degree of the denominator is greater than the degree of the numerator, we call that bottom heavy. Okay? The denominator has a greater degree than the numerator. So what that means is, as x gets bigger and bigger and bigger, you're plugging these big numbers in here, right? The x squared will always, like, in the long run, be bigger than the x. Like, you think about 1,000 squared is so much bigger than 1,000. And that, as we get towards infinity, that becomes, like, even more extreme. So what happens is, when degree of denominator is greater than numerator, we have an HA at y equals 0. Okay? Because that denominator is growing so much faster, you're dividing by a bigger and bigger and bigger number, so we're just going to approach 0 in the long run. That's how it works. Okay? That is a bottom-heavy situation. The degree of the denominator is greater than the degree of the numerator. We have a horizontal asymptote at y equals 0. In our second case, we have an even situation. So the degree of the numerator is 2. The degree of the denominator is also 2. It's like a tie. So they're kind of growing at the same pace. So when the degree of denominator is the same as degree of numerator, our horizontal asymptote happens by dividing the leading coefficient of the numerator and the leading coefficient of the denominator. Okay, so in this case, what's my leading coefficient of the numerator? It's a 5. What's my leading coefficient of the denominator? It's a 2. So in this case, it would be 5 over 2. That would be your horizontal asymptote. Degree on bottom bigger, 0. Degrees the same, divide the leading coefficients. Okay. Last situation is top heavy. So that's when the degree of the numerator is greater than the degree of the denominator. This one's easy. There is no horizontal asymptote. There is no horizontal asymptote when degree of numerator is greater than denominator. Okay? Good. So, what about the slant asymptote? How does this come into everything? So, slant asymptotes only happens in unique situations. When the degree of numerator is exactly 1 more than denominator, we have a slant asymptote. Okay? To find it, divide numerator by denominator. So in this case, I'm going to do it for this example right here, x squared minus 4x plus 7 divided by x minus 3. I'm going to do synthetic division. So we're going to do 3, and then we'll do 1, negative 4, and 7. And we will get 1, and then a 3, and then a negative 1, and negative 3, and a 4. So this would be x minus 1 plus 4 over x minus 3. That's my that's the result of my division. The x minus 1 is the slant asymptote. So y equals x minus 1. That is your slant asymptote. So part of the reason why this is happening is this expression is equal to our original rational function. And when x is getting bigger and bigger and bigger, this remainder here will become 0, right? This will become like insignificant, but this quotient will appear in the graph. Okay? All right, I'm going to leave it there.
Okay, continuing from there, let's do like a little practice. So if it's going to be a horizontal or slant asymptote, we're going to look for that degree. So the degree here, top and bottom is the same. So this is just going to be the leading coefficient of the numerator divided by the leading coefficient of the denominator, which is 2. This is just y equals 2 because the degrees are the same. Here, degree of the top is 2, degree of the bottom is 1. Since the degree of the numerator is 1 greater than the denominator, we have a slant asymptote, so we're going to do some long division here. So I'm going to synthetically divide it by 8, because that's my 0 down here. and I will get, let's see here. Sorry, I'm doing this incorrectly. 1 is negative 1658, and we will put down the 1. 1 times 8 is 8. Negative 16 plus 8 is negative 8. Negative 64, and then negative 6. So it's x minus 8 plus negative 6 over x minus 8. So again, what happens is when we set x to be a really, really big number, the function ends up looking like the quotient. So this is our slant asymptote. In fact, whatever was here on the left side is how the function would end up looking. So it could be a quadratic, it could be a different function over here, but that's kind of the end shape is going to look like whatever this is. Whereas this becomes irrelevant because we're dividing by x, we're dividing by a huge number here. So y equals x minus 8. Okay. All right, we're putting it all together. So this, we're getting towards like the end of the unit. We're putting all those 5 features together in one irrational function. The first thing you want to do when you see a rational function is you want to factor it. So we're going to factor top and bottom here. We're going to have x minus 5 times x minus 5 on top. And on bottom, we got to factor the bottom. So I like to do reverse box. So we're going to have 2x squared up here. We're going to have 5 here. We're going to have 2x. We're going to have an x. And then it's going to be negative 5 here and negative 1. Okay, so it's going to be 2x minus 1 and x minus 5. Okay, let's go through each one. Y-intercept. Always just plug in 0 for the y-intercept. F of 0. F of 0, plug in 0 top and bottom. We're going to get 25 over 5. It's 5. Okay, that's 0 comma 5. X-intercepts. So for x-intercepts, you're looking for a 0 that only appears in the numerator. So if I look at this, is there a 0 that only appears in the numerator? No, there is not. X minus 5 appears in the numerator twice, but it also appears in the denominator. Therefore, there is no x-intercept. Okay, vertical asymptote. Do we have a 0 that only appears in the denominator? Yes, we do. 2x minus 1. Right, so 2x minus 1, we're going to set that equal to 0. We're going to get 2x equals 1. We're going to divide both sides by 2. X equals 1/2. I have a vertical asymptote and x equals 1/2. Whole. Do I have a whole? Yes, I do. I have a factor that appears both in numerator and denominator. So it's going to be at x equals 5. And what we're going to do is we're going to simplify this. So we're going to cancel out these two x minus 5s and plug it into what's left over. So if I cancel out what's left over, I get x minus 5 over 2x minus 1. And I'm going to plug a 5 into that. I would get 0 over 9, which is 0. So that means my whole happens at 5 comma 0. Last step is a horizontal slant. We're going to look at the degree. The degree is the same, so it's dividing the leading coefficients, so it's just y equals 1 over 2. And that's it. Okay, so I hope that hopefully all that made sense. We have three more period. We have one more period of class, then a review day, then the test next week. So in that like extra period before the review day, we're going to spend some more time looking at rational functions, graphing rational functions. So, but take a look at the delta now, and I will see you on day 1 next week.